Section 2.5, implicit differentiation. So far, all of the functions that we have seen has been explicit in form. In other words, y is a function of x, such as y equals 5x to the fourth minus 3. And we can see that dy dx, the derivative with respect to x, would be 20x to the third. Now, finding the derivative was easy. You just took the derivative of both sides. However, sometimes functions are defined by equations in which y is not alone on one side, and it would be algebraically difficult to isolate it before taking the derivative. In these cases, instead of solving for y first, we differentiate both sides with respect to x, then isolate dy dx or y prime term. So we are going to find dy dx if 2y equals x squared plus the sine of y. What we're going to do is differentiate both sides with respect to x. So right here, I have 2y, and I'm going to take the derivative of 2y, and I'm going to take the derivative of x squared, and I'm going to take the derivative of the sine of y. Notice that's what d dx says. It says, let's take the derivative with respect to x. Now, this one's easy. The derivative with respect to x of x squared is 2x. And then I have this dx. What the heck? All right, let's go over here and think about how to use chain rule. If the derivative with respect to x of y to the first power, how would I get that? Well, the 1 comes down, y to the 0 times, this was not a function of x, so times the derivative of y with respect to x. So over here, when I take the derivative of 2y, it is 2 times 1 times dy dx equals taking the derivative of this with respect to x, 2x dx dx, because I took the derivative of an x term with respect to x, plus cosine of y, that's derivative of sine, and then the inside function's derivative times dy dx. So now we're going to collect the dy dx terms on the same side of the equation. So this one's going to come over, and I'll go ahead and leave the 2x on this side. Now notice dx, that's just 1. We can cancel that. So now we factor out dy dx, and we're left with 2 minus cosine of y equals 2x. So dividing by 2 minus cosine of y, we get dy dx to be 2x over 2 minus cosine of y. You could also write this as y prime. But this means to find the derivative on this curve, we would need both the x and the y coordinate of the points. Find the slopes of the tangent lines at 2, -1, and 2, 1 to y squared equal minus x plus 1 equals 0. Now, a little algebra will show you that you are really looking at the parabola y squared equals x minus 1. That's going to look like this. You can see that when x is 2, I have 2 lines that could be tangent, one above and one below. And you can see they're going to have different slopes. So that's what's going on. So I'm using something that you know, but you will notice that y is not a function of x because this is not a function. And that's what's really neat about implicit differentiation. We do not have to have a function for taking the derivative. So we are going to take the derivative of y squared minus x plus 1 and the derivative of this side, 0. Well, we know that the derivative of a constant is 0, so that's easy. And you do not have to show this, but what we're going to do is take the derivative with respect to x of y squared, x, and 1. This step right here is not necessary. You can go straight to this step. So the derivative with respect to x of y squared is 2y times dy dx. That is your chain rule step. Minus the derivative with respect to x of x is 1. And again, dx dx, we don't need that. The derivative of a constant is 0. That's going to drop out. And the derivative of 0, which is a constant, is 0. So now you will notice we have 2y dy dx equals 1. And solving for dy dx is 1 over 2y. What you notice here is we do not need the x-coordinate for finding the slope. We only need the y-coordinate. So at 2, -1, the slope of your tangent line is 1 over 2 times -1, or -1/2. At 2, 1, the slope of your tangent line is 1 over 2 times 1, which is positive 1/2. And if we go back up here, look at this. At the point 2, 1, see that slope, which is positive? And at the point 2, negative 1, see that slope, which is negative. Now we can go on to also find the second derivative of the function with the same work, but you will have to substitute for dy dx and simplify. You can also find equations of tangent lines once you have found derivative functions. So here we're going to find the second derivative if we know that the equation is 4x squared minus 2y squared equals 9. Now you might recognize this as a hyperbola. But anyway, we're going to differentiate both sides with respect to x. So an x term, the derivative of it is going to be 8x. You don't need to write dx. Minus, but what about this term? 2 times 2 is 4, y to the first power, times dy dx, the chain rule step, equals derivative of 9 is 0. Now we're going to find the second derivative. So what we want to do is isolate the first derivative. So this can be done with a little algebra. Notice that I can add 4y dy dx to both sides and then divide by 4y. So dy dx becomes 2x over y. Now we're ready from this step to find the second derivative. Now this is a quotient. So let us remember, low d high minus high d low over low low. Notice the notation, d squared y, the second derivative of y with respect to x. Okay? And let's simplify this a little bit. This gives us 2y minus 2x, and dy dx was 2x over y. All of this over y squared. Now that looks pretty ugly, but we at least have the second derivative in terms of x and y. Well, if I have 2y minus 2x times 2x over y, this is really 2y minus 4x squared over y. All of that is still over y squared. And I have to do some aloha. We want to clean this fraction up. This is a compound fraction. So if I multiply by y over y, what that will do when I distribute across here is give me 2y squared minus the y's will cancel, 4x squared, now over y cubed. Now, this is the second derivative, but guess what? We can actually simplify this. If you are clever, notice at the top of the page, 4x squared minus 2y squared is 9. So what do you think 2y squared minus 4x squared is? Guess what? Negative 9. 4x squared minus 2y squared is 9, so switch the order here. Requires taking a negative out so that you can switch that order. And so 2y squared minus 4x squared is negative 9. That is beautiful. Be sure you ponder that. Another way to have worked this out, if you didn't see that you could multiply by y over y, is to think about the fact that this is 2y minus 4x squared over y divided by y squared. That means getting a common denominator, 2y squared over y minus 4x squared over y, which gives me 2y squared minus 4x squared over y divided by y squared is times 1 over y squared. And you still get the second derivative to be 2y squared minus 4x squared over y cubed. It's the same as what we got in that problem, but a little bit more work. Find y prime for x cubed plus y cubed equals 3 times x times y. So this side is easy. This becomes 3x squared plus 3y squared times y prime, or times dy dx, either way, means the same thing, equals, we have a product rule here. So I took the 3x and counted that as one factor and y as the other. So 3x times the derivative of y plus y times derivative of 3x. Now, notice I want to find y prime, so I want to get these together. Let's just look at what we have. Every single term is divisible by 3, so I divided 3 out of every term, leaves this. And getting the y primes on the same side, I'm going to subtract this term this way and subtract that term this way. We can factor out the y prime, leaves us y squared minus x equals y minus x squared, and here is our derivative. And you can't do anything algebraically with that. But notice that I need both an x and a y to find the derivative. Now it says, part B, find the equation of the tangent line at the point 3/2, 3/2. Well, here's my y, can go here. Here's my x, can go here. And I have a little crazy algebra happening here. Notice that I have 3/2 minus 3/2 squared over 3/2 squared minus 3/2. Hey, we can do here in this problem what we did earlier, which is, notice, it'd be so nice if we could switch the order of one of these, and we can. If I rewrite this as negative 3/2 squared plus 3/2, notice factoring out that negative sign allows us to switch the order. So I could have gone straight from this step to this step simply by factoring out that negative. And now what you see is on top, I have exactly the same thing as on bottom. I can cancel this whole thing with this whole thing, and it leaves -1. Now, how can we be sure that 3/2, 3/2 is on our graph? Guess what? Substitute 3/2 for x, 3/2 for y, and make sure that you get a true statement. So our tangent line is going to have a slope of -1, and the equation is y minus the y coordinate 3/2 equals -1 x minus 3/2, which you can leave like that, or if you wanted to, distribute the -1, put the x and the y on the same side, and that becomes x plus y equals 3. I mean, you should be able to do that algebra. It's not necessary. It might be for you to check your answers in the back of the book because they might write it in standard form or in slope-intercept form. Now, the last question. At which point is the tangent line horizontal? Let us recall. We get horizontal tangents when the numerator of our derivative is 0 and the denominator is not. So the numerator is going to equal 0 when y equals x squared. And I need to find the points. So I'm going to substitute x squared for y in my original equation. So when I do that, I get x cubed plus, substituting x squared there, cubed, has to equal 3 times x squared. Now, if you look at that, that gives me x to the third plus x to the sixth equals 3x cubed. And that's going to give us x to the sixth minus 2x cubed. Well, I can solve that. That's not terribly difficult. I have greatest common factor of x cubed. And so factoring out x cubed leaves x squared minus 2. So this is going to equal 0 when x is 0, or when x cubed minus 2 is 0. And x cubed minus 2 is 0 when, add 2, take the cube root. X is 2 to the 1/3. So it appears that we're going to have a horizontal tangent line when x is 0, so that gives me the point 0, 0, or when x is 2 to the 1/3, and if x is 2 to the 1/3 and y equals x squared, then y would equal 2 to the 1/3 squared, or 2 to the 2/3. But what happens if x is 0? Then y is 0, and my y prime is 0 over 0, and we know we can't have that. So the only answer is this one. How can I confirm 2 to the 1/3 and 2 to the 2/3 is on the curve? I can go to my equation, x cubed plus y cubed is equal to 3xy, and see when I substitute in if I get a true statement. 2 to the 1/3 cubed is 2, plus 2 to the 2/3 cubed is 2 squared, and 2 plus 4 is 6. Come over here, 2 to the 1/3 times 2 to the 2/3 is 2 to the, add the exponents, 1/3 plus 2/3, which is 3/3. So I have 3 times 2, which is 6. So that works nicely. Another question. Is my denominator 0 at 2 to the 1/3, 2 to the 2/3? Is y squared minus x 0 at this point? Because I cannot have 0 over 0. So 2 to the 2/3 squared is 2 to the 4/3 minus 2 to the 1/3. Well, you know you can't do that. What we can do is factor out 2 to the 1/3, and that leaves 2 minus 1, which is 1. So 2 to the 1/3 is not 0, so my denominator is not 0 at this point. So y prime does equal 0 at 2 to the 1/3, 2 to the 2/3. Your TPs for section 2.5 are 1, 5, watch the product rule, and it follows a negative sign. 11 and 13.